Okay, I want you to try and picture something with me for a second. It's pretty counterintuitive.
All right, I'm intrigued.
Imagine you have an object and you can completely fill it with a very precise small amount of fluid. Let's say about pi liters, so just over 3.
Okay, so a finite amount. I can fill it up.
Exactly. But, and here's the twist, you could never paint the outside surface, no matter what, not with all the paint in the world.
That sounds like a riddle or a geometric impossibility.
It does, doesn't it? It feels like it breaks our basic intuition that if something can hold a finite amount, it must also look finite.
And that's the whole paradox of what's called Gabriel's horn, or historically Torricelli's trumpet. It was first studied by Evangelista Torricelli way back in the 17th century.
And that's our mission for this deep dive, to really unpack this mathematical truth. A shape with an infinite surface area.
But a completely finite volume. It's a dive straight into the weirdness of infinity.
So to get our heads around this, what exactly is this horn?
It's actually pretty simple to describe. You take the graph of the function y equals 1 over x.
Okay.
You start at x equals 1, and then you just rotate that curve around the x-axis in 3 dimensions, extending it out infinitely.
So as the horn gets longer and longer, its opening gets narrower and narrower.
Precisely. And that speed of shrinkage, that's the key. The function 1 over x is what determines everything.
Because that's what calculus uses to figure out the volume in the area.
Exactly. When you calculate the volume, you're basically summing up an infinite number of tiny, thin disks. And because the radius shrinks so quickly, the formula uses 1 over x squared, that whole infinite sum. It actually converges.
It stops. It adds up to a final number.
It adds up to exactly pi, a nice finite number.
Yeah.
But with the surface area, things get strange.
Let me guess, the formula is different. It doesn't shrink as fast.
You got it. The calculation for the surface area relies on a term that shrinks more like 1 over x. And that's just not fast enough. That's some diverges.
So it just keeps growing forever.
It approaches infinity. It's like what the thinker Nicole Oresme hinted at centuries earlier, the idea that an infinite diminution of one dimension compensates for the infinite increase of the other.
Wow. So the math is solid. But I can only imagine the philosophical arguments this caused in the 17th century.
Oh, it was a huge dispute. This became known as the painter's paradox, and it really shook things up.
I bet.
You had thinkers like Thomas Hobbes who basically said this proved math was relying on a fiction. He argued that infinite must just mean indefinite.
He couldn't reconcile it with the real world.
Not at all. But then you had others, like John Wallis, who just embraced it. For him, it was proof of the power of this new thing called calculus.
So how do we resolve it? I mean, why can you fill it with pi liters of paint, but you can't use that paint to cover the outside?
Well, the paradox completely vanishes the moment you think about physical paint.
What do you mean?
Torricelli's theorem is about a pure mathematical volume. But physical paint has thickness, right? It's not zero.
Ah, I see where this is going.
Even if it's microscopically thin, when you multiply that non-zero thickness by an infinite surface area, the volume of paint you'd need becomes
infinite. You'd need an infinite volume of paint to cover an infinite surface. That makes perfect sense.
It does. And there's another physical limit, too. Eventually, the throat of the horn becomes narrower than a molecule of paint, so you couldn't even get the paint down there to begin with.
This deep dive into complex ideas is brought to you by Silk. If you need help with AI training, automation, integration, or software development, or even just figuring out where AI agents could make the most impact for your business or personal life, check out embersilk.com for all your AI needs.
You know, before we wrap up, it's worth asking the opposite question.
Which is?
Could a shape exist with a finite surface area, but an infinite volume?
That sounds even more impossible. Like having a gas tank that holds an infinite amount of gas, but you could, I don't know, wrap your arms around it.
And what's so powerful here is that mathematics gives us a definite answer. No, the converse cannot happen.
Really? It's proven.
It is absolutely proven. If a surface of revolution has a finite surface area, its volume is mathematically guaranteed to be finite too. It shows that math establishes these profound, certain limits on how reality can work.
So the real takeaway isn't the confusion of the paradox, it's the clarity that comes after. It's the power of our intellect to actually quantify and understand the infinite.
Exactly. Even something that seems limitless can have discoverable rules and definite bounds.
And that's just an incredibly optimistic thought. Even in the biggest unknowns, we can find certainty. If you enjoyed this deep dive, please subscribe to the show. And hey, leave us a 5-star review if you can. It really does help get the word out. Thanks for tuning in.